lollipop, lollipop, oh, lolly, 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 lollipop, lollipop, oh, lolly, 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 lollipop, lollipop, oh, lolly, 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 lollipop.
Boom, boom, boom.
Lollipop, lollipop, oh, lolly, 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 lollipop, lollipop, oh, lolly, 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 lollipop, lollipop, oh, lolly, 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 lollipop.
Boom, boom, boom.
Call my baby lollipop, tell you why. His kiss is sweeter than an apple pie. And when he does a shaky rock and dance, man, I haven't got a chance. I call him lollipop, lollipop, oh, lolly, 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 lollipop, lollipop, oh, lolly, 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 lollipop, lollipop, oh, lolly, 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 lollipop.
Finally tonight, a new era in astronomy. NASA releasing a full batch of images and data from the massive James Webb Space Telescope, providing a first look at the cosmic mysteries yet to be untangled by the largest and most powerful space observatory. And who better to help us untangle this tonight than America's top astrophysicist, maybe the world's top astrophysicist, Neil deGrasse Tyson, joining us right here in person.
What we're actually looking towards is a galaxy cluster halfway to the edge of the universe.
Okay.
And it has a very strong gravitational field surrounding it. Meanwhile, galaxies behind it, these that are curved into arc shapes, they're light passing through the universe, minding its own business. It sees this distortion in the fabric of space and time, and it curves in response to it. Einstein predicted this.
There could be planets. There could be another sun,
these are entire galaxies of commensurate rank and privilege, such as what the Milky Way is.
And we can't even count them.
And this is just, and you know how big this is on the sky? If you take a grain of sand and hold it at arm's length, the patch of sky covered by the grain of sand is what you see here. So this is just stupefyingly detailed.
I want to keep feeding this. Give me another image here. We can't stop this. Come on. What else do we have here next up? Let's see what we're seeing here. This is a beautiful one. This is the Carina Nebula.
Once again, the stars that are nearby. By the way, these spikes occur because of, it's called diffraction spike. Light, as it passes through the spider mounting of the secondary mirror, diffracts around it. So there's nothing cosmic about that. It's a hardware artifact within the telescope.
And then this is
an actual gas cloud, and because the telescope is tuned for infrared, infrared has good penetration depth into gas clouds. By the way, it's the same reason why your fog lights on your car are more red and amber than blue. The more red you are into the spectrum, the deeper into clouds you can penetrate. And when you do that, you have access to places where stars are being born, as well as planetary systems around them.
Are these colors enhanced at all by NASA, or is this what the telescope is seeing?
Okay, you want to go there? We'll go there.
I want to go there.
Let's do this. Yeah. Okay, so in your eye, you have red, green, and blue RGB sensors in your retina. And what happens is, what we define as visible light is the light that comes through and is detected by these three. Those get combined into a single color image of what you see in your brain.
Okay.
Now, think about that. This entire telescope is tuned for the infrared. You can't see infrared.
Okay.
But what the telescope does is it can take images in 3 different bands, separate bands of the infrared. Then you hand it an RGB and create a color picture, which is the color you would see if your eyes could see infrared. So it's authentic and legit. It's authentic and legit.
And we knew that selecting the images was just the beginning, that we would need a trained eye to take these exquisite data and pull out the beauty and the science potential. So here's Jody Pasquale and Elisa Pagan to tell you about how they processed these beautiful images. And they have it up downstairs. I think they missed some of that beginning.
We're basically translating light that we can't see into light that we can see by applying color like red, green, and blue to the different filters that we have from Webb. And the reason we want to color the images is because there's actually more that you can get, more information that you can get from the image if you see it in color.
So it's a matter of picking and choosing filters and colors that enhance the details and the structure in the image itself.
The shortest wavelengths of infrared light and assign those blue colors, and then move our way down to green and red as we go to longer and longer wavelengths.
And then we additively combine those together to get our full color image.
But there is a lot of aesthetics that are involved in this. And painstakingly going through and cleaning these images up with an attention to detail, a level of detail like at the pixel level in every image.
So when I'm working on the astronomical data, it is this sort of marriage between art and science. When you're choosing colors for the filters, you really are trying to show the different details and the processes that are happening in the astronomical images. But at the end of the day, you want it to be very compelling. You want it to be very compelling.
You want it to be very compelling.
You want it to be very beautiful because space is beautiful.
Today we're here with visualization specialist at the Harvard-Smithsonian Center for Astrophysics, Joe DePasquale. Joe, welcome to Flyby.
Thanks, Chris. Thanks for bringing me in here.
So when there's a press release, when NASA comes out with a new finding or new images, essentially you're taking data to create an image to be a part of that press release.
You know, in general, the public's perception of how these images are created, people tend to think it's like a camera, right? You just shoot a picture and there it is. But with astronomy, it's very different. What we get from the telescopes is just data, and in most cases, it's just a black and white image with a lot of artifacts, and it's a really messy thing that needs to be cleaned up. It has to have color applied to it. We're not inventing color when we do this, but we do have to make decisions about how to color the images.
You're actually taking data and then you're applying color to it, but there's not necessarily rules and guidelines, traditionally speaking, with how best to apply color. But you mentioned there's certain rules with regards to heat that you take a look at that informs how to color images.
Yeah, so my group at the observatory has been involved in the past few years with a project called Aesthetics in Astronomy, where we've been interviewing the general public and giving them surveys to see what their perceptions of astronomical images are, how they interpret the colors that are used in those images and what it means to them. And one of the things we found that's really interesting is, say for example, you do a Google search for cool colors, cold things, like what would you expect to find?
Generally things blue, light blue, dark blue.
Right, so that's like a culturally conditioned thing.
Sure.
That people expect cool things to be bluish and warm things to be red or yellow. And in physics, that's actually the opposite. Hot things they get bluer and bluer and bluer till they get to white. And as you cool them off, they turn redder in color. So we try to use that information. We know that people have this perception of what colors mean, but we also want to stay true to the physics of the objects that we're looking at. And so I typically choose cooler colors for X-ray in these images.
The building blocks of your story is data, like ones and zeros.
That's right.
But how do ones and zeros become something that we're looking up, up here on the board?
Well, it depends on the type of telescope you're working with, but with X-rays, for example, the Chandra X-ray Observatory has these amazing mirrors that can focus X-rays with such high precision. It has these exquisite mirrors. They're actually very different. The technology to focus X-rays is very different from any other telescope technology. It's essentially barrels, glass barrels. Instead of being like a big mirror, these barrels do something called grazing incidence, where X-rays come in and they bounce off the mirror, almost like skipping a stone on a pond. And then they're guided down this long, it's called the optical bench, to the detectors. And that where the detectors are, they're sensitive to X-rays. They're just CCDs, like in a cell phone camera. Mm-hmm. So they have CCDs in them that then take that data. It takes readings of X-ray light. An X-ray photon hits the detector. We know the energy of that photon, where it struck the detector, when it hit the detector. And all this information then gets transmitted to the ground. And we can reconstruct an image from that data.
What are we looking at over here? How far away is it? And then maybe talk to us a little bit about your process in creating this image.
Right, so this is a galaxy. This is called M106. The interesting thing about this galaxy is you can see this sort of weird wavy shape in the middle of it. If you're looking at this in optical light, you don't see that at all. There's no indication of this strange shape, unless you're looking at a very specific wavelength of light. And what that actually is, it's called the anomalous arms of M106. And in this image, we're seeing X-rays in blue and then radio wavelength in purple. And then to balance all that out, we have the optical data from the Hubble Space Telescope and that's in sort of a kind of a gold color, and then infrared data from the Spitzer Space Telescope in red.
You know, what informs you to actually make, you know, this white? I mean, I assume like that's the hottest part, correct?
Right. So this is actually a really good example because this image started with a press release image from the Hubble Space Telescope, which was a very colorful image. It was a full 3-color image, what we call it, red, green, and blue. Our group is very concerned with color confusion for the general public. We want to be able to say that things that you see in this image that are colored blue are X-rays. And so if you have an image that has blue from optical and blue from X-rays, then there's some confusion as to what's what in the image. And so I made a creative decision to take the full color image from Hubble and decompose it into its constituent colors and then recombine it in a way that made room, so to speak, for other colors to show through. So the Hubble data is actually sort of reduced down to a lesser palette of colors, and that frees up color for other wavelengths. And so the red you can see comes from the Spitzer there, that's infrared, and you wouldn't really be able to see that as clearly if we kept all 3 colors from the original image. And then of course you can see now that anything that's blue in this image is coming from the X-rays. And the reason that the center becomes white is because that's where all of these colors sort of come together. And wherever you have that, you have white.
How accurate would your image be to how this galaxy actually looks?
Well, what I can say is that we're not making anything up. You know, this is real data. This is what the telescope sees. And like I said before, a telescope can see things that our eyes can't see. Like for example, the Chandra mirrors can focus X-rays to such precision that it's equivalent to being able to read the letters of a stop sign from 12 miles away. So we can focus in a way that our eyes can't with these telescopes. But if we could get close enough to it to be able to see it like this, of course these colors wouldn't be there because this is stuff beyond the visible wavelengths.
Sure.
But the colors that our eyes could see, it really would just kind of look like a faint smudge. If you look online, do Google searches for images of the Milky Way, people have taken some really incredible ones, and they look as cool as some of these images because we live in the middle of a galaxy and we can look up and see that, but our eyes just can't resolve that kind of detail or color.
But we're starting to understand, you know, at least the infinite possibilities that are going on in the universe. An image like this starts to allow us to at least imagine, correct?
Yeah,
like
absolutely.
what's out there?
I think these kinds of images, they inspire people to wonder. They sort of speak to a universal truth of, you know, that we all are part of this. We look up and we see these things. They're bigger than us, but we're also a part of this. And you know, an image like this is just mind-boggling. This star down in the corner is most likely a nearby star in the Milky Way, but that's the only thing that is within our Milky Way in the image. Everything else here, you know, this is like a tiny patch of the sky that you're looking at with a telescope, and you're letting it sit there and integrate light over and over for a very long period of time, and you're pulling out all these galaxies. You know, most of the bright points in this are galaxies.
And it's just one focal point out into the universe of,
right.
You know, it's saying this is going
Like
on everywhere,
exactly.
everywhere. And then, so when you make these discoveries, and certainly we've been finding more and more as we go along, like how does that make you feel, like in your dedication to your craft and everything, like that you know, the universe is so infinite that we'll perhaps never fully understand it?
This is really what got me into astronomy in the beginning, was like images. I can't say like these because when I was a kid they didn't have images like these. You know, Hubble was launched in 1990, so we didn't really get to this kind of detail in astronomical images until that point. But I do remember seeing the first images from Hubble after the mirrors were fixed and just being completely awestruck. And you know, I'd always had an interest in astronomy, but that just like did it for me, and I knew that that's the direction I wanted to go.
And then the fourth image that we have over here, you have a 2D representation of the image.
So this is Cassiopeia A. This was actually the first object that Chandra looked at after it was launched, the first light image. And in that image, it made a discovery. This white dot in the center here is actually a neutron star that was theorized to exist. You know, this object had been known to exist before Chandra looked at it, but we never knew that the neutron star was there or not. And Chandra discovered that in its first image. And then we went back and we've looked at this many, many times since then. You know, Chandra's been in orbit now going on 17 years. So we have something like 14 days worth of data of integration time on Cass A. It's 11,000 light years away. So this is one where I actually do know the distance to it. It's 10 light years across. And the colors here, this is all X-ray as opposed to these images, which are, you know, combinations, multi-wavelength images. This one is just pure X-ray. And the colors in it actually come from, so there is a certain ordering to the way colors go in these images. And what we'd like to do is follow a chromatic ordering. So we take the X-ray data that spans many energies of X-rays and break it down into low energy, medium energy, and high energy, and then assign those channels colors. So you get red, green, and blue. And when you combine those together, you get the full spectrum of light. And that's what you get when you combine this image that way with low, medium, and high energy.
So you're kind of like an intergalactic art director in a sense.
In a sense, yeah.
How does that make you feel?
I feel like there is a certain power there to be able to take this data that is just black and white and give it some kind of color that then informs, you know, the scientific interpretation of what's going on in this image. This is an exploded star, and you know, if you've ever watched Mythbusters and you've seen those slow motions of explosions, right? You see this like shock wave move out,
yeah,
and it's really cool to see that. Well, that's what this blue is all the way around this object. That's a shock wave expanding out into space.
Do you love what you do, and why do you love it?
I love what I do. I love having the opportunity to work on things like this, to make these images. Like I said before, I feel like I'm contributing in a real concrete way to inspiring other people to be interested in space and astronomy. So, I'm working on a project right now to help middle school children understand the way that we focus X-rays with the telescope. So it pulls everything together. So I just feel really fortunate to be able to, you know, do all that stuff with my job.
Well, we thank you so much for taking the time to talk with us today.
Thanks for bringing me in.
Thanks again, Joe.
Christmas Day, when others long ago peered up into the sky and saw stars. But it's also another millennia before that a shepherd grazing his sheep would look up at the night sky. He became a poet, and he penned the words, "The heavens declare the glory of God, the firmament shows his handiwork." That shepherd, that poet, became king. And those immortal words in Psalm 19 encapsulate the expressions that we have today. The handiwork of God as we peer back in time over 13 billion years ago, capture the light from the very beginning of the creation. My congratulations to the team. My congratulations to NASA, to our partners. Go James Webb Space Telescope. God bless you, and God bless planet Earth.